Well, Happy New Year to everybody and welcome back to second semester. I'm really excited to move ahead in calculus with you. We did 4 chapters in first semester and we're going to press on and do 4 more chapters this semester and really get you set up for next year. If you're going to continue studying math at college or here at Valley next year, getting you set up for that. So chapter 4 continues with the derivatives we were working on, and you might need to dust off some of the cobwebs. It's amazing how quickly our brains forget what we don't use, and so some of the derivatives we were working on earlier you may have forgotten already. So don't worry, it'll come back quickly as we review this. So today what we're going to talk about is something called an extrema. An extrema is a high and a low. If you're having, extreme temperatures or extreme emotions, okay, you're feeling high, you're feeling low, you're feeling warm, you're feeling hot, whatever, that's an extrema. So we're going to talk about that today and how to test for them and how to find them. So extrema are classified in 2 different ways. We have maximums and we have minimums. And so a maximum would be the highest y value on the interval of a function. All right, so you can have lots of different y values, but a maximum would be the highest. The minimum is going to be then, by converse, the lowest y value on an interval of the function. An interval starts at point A and ends at point B. Okay, so those are the 2 different categories. When I say extreme values, that's what I'm talking about. So looking at a graph, we can identify extreme values just by looking at it. So we have 2 maximums here. Okay, those are the y values of these peak points right here. And notice that they are differentiated between a local and an absolute. An absolute is the highest of the high. Okay, nothing else is higher on this interval from point A to point B. Okay, it is the highest of the high. A local maximum is pretty high. It's high in its area, so its own locality, but it is not the highest. Okay, so think about like if you've got a couple different gangs or something, and if you've got somebody who is the lead, the chief, the head of the jefe of this gang in their neighborhood, they are the highest in that neighborhood. But if you go a little bit bigger or to a bigger city, you might have someone else that is the highest, higher than them. And so it's the idea of being high within your own sphere, within your own area, but not necessarily the highest. And then we've got 3 different minimums here. We have, because they are all the lowest value. But then you've got the absolute is the lowest of the low, right? Okay, so if this is the lowest and you compare it, it is lower than any of the other maximums, whereas the minimums, whereas the maximum here is higher than any of the other maximums. So absolute versus local, they can be at endpoints as well. So you can easily visualize where these are. That leads us to a theorem which says that maximums and minimums have to exist. They are guaranteed if f of x is continuous and you have a closed interval from A to B. Okay, you are guaranteed at least 1 max and min. There might be more, like we saw, there could be 2 maxes, one is the absolute and one's the local. There could be 2 or more mins. But you're guaranteed to always have at least 1 max and at least 1 min if the function is continuous and closed. If it's not continuous, you're not guaranteed, and if it's not closed, you're not guaranteed. So the extreme values are divided up into 2 categories. Always the endpoints. So you would have point A which is the left endpoint, and then you would have point B. And point B is always the right endpoint. So you've got, those could be the candidates for extreme values. The maximum might happen, or the minimum might happen on the endpoints. You also have critical points, which are what are called interior. They have to be between point A and point B. Okay, so somewhere in the middle. And there are two kinds of critical points. Just like there's two endpoints, there's a point A and a point B. Those are the two endpoints. There are two kinds of critical points as well. There are horizontal critical points, where you would have a horizontal tangent. There are also cusps, corners, that could be critical points. So there are two kinds of those. So we can find those just by looking. So let's look, what would that look like? Okay, so setting f prime of x equal to 0 is where you're going to see horizontal tangents. Okay, you're going to locate these, and remember this is an x value in the interior domain of a function at which f prime of x, the derivative, is equal to 0. So when you look for it, you're going to look for a maximum peak that has a horizontal tangent like that. Or you're going to look for a minimum curve that has a horizontal tangent skimming across the bottom. That could be a critical point. Or when the derivative does not exist, you're going to have a corner or a cusp. So that could be where you have the corner of a graph. And that would be, or where you have a cusp. Remember, cusp kind of looks like a wave, like that. That also is a critical point. So visually, you got to know what you're looking for. So let's practice here. Right here, we see a cusp. And we'd say, oh, it's a critical point because it's a cusp. And right here, we would say, oh, it's a critical point because it's a corner. This point right here is neither. So it is not a critical point because it's not a corner or a cusp or a horizontal tangent. In the next picture, we have a horizontal tangent right there. So that's a critical point. And then we have another horizontal tangent. So that is also a critical point. But we have neither going on at C, so that is not a critical point. So in both of these pictures, A and B are both considered critical points, but C is not. Again, here's another picture. We've got horizontal tangents, and so those are critical points. But C is not. And then in this one, we have a cusp, and we've got a horizontal tangent. But C is not either, so it's not a critical point. Also, you'll also have critical points at all the endpoints. So both of those would also be critical points. So that's the endpoint on the left, and this is the endpoint on the right. You'd have critical points here. And on the other picture, you would have critical points on the endpoints as well. Okay, so if I would say, count how many critical points there are. You always count the endpoints, and then you count any cusps or corners or horizontal tangents. Always. So, can you find critical points without looking at a graph, though? Right? So it's easy to find a critical point when you're just looking at a graph. But what if you don't have a graph to look at and you can't make a graph on your calculator? Can you find the critical points a different way? And that's where calculus comes in. It doesn't take calculus to be able to find them visually, but to find them algebraically, or what we call analytically, that's where it takes calculus. So you're going to find critical points when you set the derivative equal to 0. So you're going to set the derivative equal to 0, and then you're going to solve. And that will find critical points for you. It will find the horizontal tangents. And if you want to find corners or cusps, you set the derivative equal to undefined, which means you're setting it equal to 1 over 0. And then you cross multiply before you solve. And that will find you any corners or cusps. So without looking at a graph, you are going to find the endpoints and you are going to find the critical points. So that is what's called the candidate's test. You will be given a function f. You will also be given a closed interval. Those are the endpoints. Then you are asked to find the x value for all of the candidates. So the candidates are the critical points, which is when you set the derivative equal to 0 or equal to does not exist, and you check the endpoints. These are x values. So you find all the x values of the endpoints and the critical points. Then you find all the y values for each of those x values. X values first, then find your y values. Then you start comparing the y values and you find the highest of the high. You'll have some that are higher than others. Find the highest of the high. That will be the absolute maximum. And then find the lowest of the low. That would be the absolute minimum. This is called the candidate's test. So let me give you kind of a flow sheet to help you visualize how that's going to go. So you'll start with your endpoints. Your endpoint would be point A, and you need to find the y value there. And then you have point B, and you need to find the y value there. All right, then the endpoints are done. Then you do your critical points. You want to find the derivative first. And then you're going to set the derivative equal to 0, and you're going to set it equal to 1 over 0. Solve. After you've solved, you want to find the y value for each of the solutions that you found. So you start with the endpoints, you find their y values. Move on to the critical points. Use the process of finding the critical points and then find the y values that go with that. When you're done with all of that, you're going to compare the y values to each other. And then you're going to find the absolutes from that. Okay, so you'll have some high ones and some low ones. The highest of the high would be the absolute max. The lowest of the low would be the absolute min. Okay, so that's just sort of a little drawing to help you through the process. So let's actually do this in each of those steps. So use the candidates test to find the absolute max and min of the following function. So we're going to start with the endpoints. We'll start with point A. So the endpoints are based on the interval 0 to 6. So x is 0 is point A. And point B, x is 6. So that's all that we're looking at. We're looking at from 0 to 6. And we want to find the y value that goes with each of those. And we simply plug 0 in for x to find the y value. So y equals 100. Then we will plug in x is 6. Okay, so we'll take x is 6 and plug it in here. And we get y equals negative 134. So we've got one high and we have one low. All right, now we're going to move on to the critical points. In order to find the critical points, we first have to start with the derivative, so f prime. And we'll find the derivative using our derivative rules. The derivative of x cubed is 3x squared. The derivative of minus 75x is negative 75. and then the derivative of 100 is 0. We'll set this equal to 0, and we'll set it equal to undefined. So 3x minus 75 equals 0, and 3x squared minus 75 equals 1 over 0. And I'll put a 1 under it so I can cross multiply. When I solve this and get x by itself, I get x equals plus and minus 5. When I solve this one by cross multiplying, I get 0 equals 1, which is not true. 0 doesn't equal 1, so there's no solution for that one. So now I want to find the y values that go with the x values that I just found. So what would y equal then? So I got to plug 5 in, and then I have to plug in negative 5. I'll get negative 150 when I plug in 5, and I'll get positive 350 when I plug in negative 5. All right, so now I want to compare the points I have. I've got 0, 100, that's a pretty high point. I have 6, negative 134, that's a pretty low point. From this one, I've got 5 with negative 150, and I have negative 5 with 350. So I've got one low and one high as well. However, let's go back and look at the interval is from 0 to 6. So these points have to be within the interval, starting at 0 for x and ending at 6. So 5 is fine. 5 is between 0 and 6. But negative 5 is not, and so this point is thrown out because it is not an interior point. It's not between 0 and 6 for an x value. So then I'm ready to identify the highest of the high. And the highest of the high is 0, 100, since I threw out the 350. And then I want to identify the lowest of the low. I have two minimums, but only one of them is the lowest, and so that would be 5, negative 150. So that would mean the negative 134 is a local minimum, but it is not an absolute minimum. So that was the candidates test applied to a pretty straightforward polynomial. So let's try another one. Let's do the candidates test to find the absolute max and min on a logarithm. The beginning is still the same. We want to do the endpoints first. So my endpoints are point A, where x is 2, and point B, where x is 5. So I want to find the y value that goes with each of those. If I plug 2 into the equation, I'm going to get the natural log of 3. If I plug 5 into the equation, I'm going to get the natural log of 9. Now the natural log of 3 is the low, and the natural log of 9 is the high so far. Now we want to go and check the critical points. In order to do the critical points, we have to find f prime. So we have to remember how to find f prime. So for a logarithm, it's 1 over. Okay? And so the logarithm then is 1 over, it's always the parentheses, 2x minus 1, and it's always the natural log of the base, and the base in this case is e. And then because of the chain rule, this is the natural log of, and anytime we say of, we need the chain rule. We have to take the derivative of the parentheses 2x minus 1, which is 2. So the natural log of e is 1, and so this simplifies to be 2 over 2x minus 1. That's not a reducible function. You can't take the 2's and reduce it because it's a subtraction problem, and so this is the end. So now we want to take our derivative, and we take 2 over 2x minus 1, and we set it equal to 0. And we also take 2 over 2x minus 1, and we set it equal to 1 over 0. Setting it equal to 0, we'll find any horizontal tangents. Setting it to 1 over 0 will find any corners or cusps. I'm going to put it over 1 here so that I can cross multiply. And when I cross multiply, I get 2 equals 0. Well, 2 is not equal to 0, so there's no solution there. In the bottom half, I'll also cross multiply. That will give me 2x minus 1 equals 0, which means x is half. So then I check my interval. X is half is not between 2 and 5. Okay, x is half is outside of that, so it is not an interior point, so I throw it out. So I don't have any additional solutions there either. So I only have my original endpoints. And so then the absolute max is the higher of the two, so that would be 5, comma, ln 9, and the absolute min would be the lower of the two, so 2 and the natural log of 3. So we've practiced this with a polynomial, and we've practiced it with a logarithm. Let's see what other kind of derivatives we can practice with. Use the candidate's test on this exponential function. So our endpoints here will be -1 and 3. And I want to find the y value that goes with both of those endpoints. So I'll plug in -1. That will give me 5 to the -5. If I plug in 3, I will get 5 to the third. Now 5 to the -5 is a very small number, so it's going to be really low, 0.000034. 5 to the third is a bigger number, 125. So now we've got a pretty low number and a high number. Now we want to check the critical points. We have to remember how to do a derivative. So you may have to go back and look at old notes or in your Notability or maybe study guides or something, but this is an exponential. So the rule for an exponential is the derivative starts out as itself, and then it has an ln of the base, and then it has the derivative of the power, which is 2x. So I am going to set this equal to 0, and I'm going to set it equal to 1 over 0. Remember, setting it equal to 0 finds any horizontal tangents. Setting it equal to 1 over 0 will find any corners or cusps. When I set it equal to 0, it's the same thing because of all the parentheses as setting each piece equal to 0. So 5 to the x squared minus 6 being set equal to 0, ln 5 being set equal to 0, and 2x being set equal to 0. So it's 3 different ones, just like if you had factors in parentheses and you would set each of those equal to 0. This is no solution because an exponential can't be equal to 0. This is no solution because the natural log of 5 is not equal to 0. And this one is x equals 0. Check the interval, and x equals 0 is between -1 and 3. So I'm good to go. So I should be able to find the y value that goes with that. So if I plug 0 into the original function, I get 5 to the -6, which is another really small number. It is 0.000064. Okay, let's see. I think, let me count. How did I do here? Oh, I have too many zeros in this one. Let's fix that. There should only be 3 zeros. 3, 4. Okay. All right, then I work on cross multiplying here, so I am going to put an over 1, and then when I do my cross multiplication, I will get 1 equals 0, which is not true, so there's no solution. All right, so now I check for the lowest of the low and the highest of the high. So my absolute max is clearly 3 and 125. Okay, that's higher. Now I check my really small numbers, and one of them is lower than the other, and that is this one over here. So that would be 0, comma, 5 to the negative 6, and that is my absolute min. So let's find it on a trig expression. So the beginning is always the same. You'll always check your endpoints first, and my first endpoint would be negative pi sixths, and my second endpoint would be pi fourths, and I'll check the y values for both of those. So the cosecant of negative pi sixths is the reciprocal of the sine of negative pi sixths. So if you remember your unit circle, remember your trig, that is negative 2. That's the reciprocal 1 over negative 1/2. And then pi fourths is the reciprocal of the sine, so that's 2 over rad 2. So the negative one is going to be the lower one, and the positive one will be the higher one. Now let's check our critical points. F prime, so the derivative of cosecant, when we do trig, any cos have a negative, and the derivative is cosecant x cotangent x. Now when we set that equal to 0, I'm going to recommend that you change those into their identities. So it would be, instead of cosecant, it's negative 1 over sine of x. And then cotangent is cosine over sine of x. So it's going to be easier if you change those before you set it equal to 0. So I'm going to set that equal to 0. I will also do the work of setting it equal to 1 over 0. All right, when I do the 0, I'm going to do 0 over 1. It makes the cross multiplying easier. All right, so let's cross multiply. That will give me negative sine x, excuse me, get that right here, negative cos x equals 0. You might want to rewrite this, so instead of having 2 sines, you might want to put sine squared, and then just have the negative kind of be out front. That might be easier, like that. And let's do it that way for the other one also. So let's combine, so we have sine squared and negative. All right, when I solve negative cos x equals 0, I divide both sides by negative 1, and then I figure out the cosine there using my unit circle, and I get the answer of x equals pi halves, or half pi. Now check your interval. Pi halves is too big. It's not in the interval between negative pi 6 and pi fourths, and so that is not going to be a viable solution. All right, then we come back and we're going to cross multiply the other one. And when I cross multiply that, I get sine squared equals 0. So I square root both sides and I solve, and x is 0. And this one is in the interval between negative pi 6 and pi fourths, so we can find the y value for that. Okay, and the y value for this is infinity. All right, now this should be a little bit alarming to you, that we get infinity when we plug 0 back into that. So then we got to think back to the original equation. The cosecant of x. If you can picture the cosecant of x graph, it's a graph that looks like this. It has upper parts, it has lower parts, like this, and it has asymptotes that go in between, like this. Cosecant of x is not continuous. It's broken. It's broken with asymptotes into lots of different pieces. Therefore, if we go back to almost the very beginning slide of this original thing, all the way back, it has to be continuous within the interval. Otherwise, you won't have a max or a min. And so we come back and we answer this question that there is no max or min because cosecant is not continuous. So since cosecant x is discontinuous, there is no absolute. So watch that. Okay, make sure it's continuous on your original interval. That may have saved us the work. Okay, if we would have noticed that right at the beginning. All right, last one. This one is continuous. Okay, 3 to the times x to the 2/3. So this is for sure continuous. All right, so let's check our endpoints. So I won't make you have to go through the work of doing something that's discontinuous. All right, the endpoints. So x is -1, and also x is 2. So the y values for those. So let's plug in. X is -1, and when I put that into the equation, I get 3. And then when I put in x is 2, I'm going to get 3 times the cube root of 4. So the 3 is lower than the 3 times the cube root of 4. That's going to be the higher one. All right, let's check the critical points, which means we need our derivative, f prime. And do you remember how to do these derivatives? You move the power to the front and then subtract 1 from the power. So that would be 2/3 in front of 3 to the x, and now we move the power down 1, which is -3. Okay. Then we can reduce. This 3 reduces that 3, and so we have 2 over the cube root of x. So we'll set that equal to 0, and we'll set it equal to 1 over 0. In fact, I'm going to do 0 over 1. It always just makes the cross multiplying easier. So cross multiply. And when we do that, we're going to get 2 equals 0, which is not true, so no solutions there. And then when we cross multiply here, we'll get cube root x equals 0. And that is solvable, so x is 0. Check your interval. Okay, x is 0 fits in the interval, so that's good. So now we can find our y value. And the y value, if we plug it back in, is y is 0. So now we can identify the absolutes. So the absolute max, the highest value of all, is 2 and 3 times cube root 4. That is the highest number. Our absolute min, now we did have a 3, which was lower, but the 0 is lower still, and so our minimum is 0, 0. So overall, when you can identify them visually if you're looking at a graph, but without a graph, you'll have to do some calculus to compare the values of the endpoints to the values of the critical points. making sure that the function is continuous, and making sure that your values fall within the closed interval. So work your way through that, and then tomorrow we'll do a little bit more work on identifying absolute maxes and mins. All right, thanks, and good luck with your start to second semester.